KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Neet, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we will focus on Davison-Germer experiment. Okay, from this chapter, dual nature of light, we will focus on Davison-Germer experiment. Okay, right. And if you look at this chapter, from starting onwards, we focused on the natural phenomena, photoelectric effect. After that, we focused on, wave nature of matter. And before that, we discussed wave nature of radiation. Okay, that is these are the things we discussed from starting of this chapter. Okay, right. And from the starting of this chapter, dual nature of light, we discussed some of the important definitions, right, and some of the important observations and Einstein's photoelectric equation. After that, effect of intensity and frequency of light. Okay, after completion of that, we discussed both particle nature of light and wave nature of light. Okay, at that after completion of that particular thing, we discussed, that is, now we are going to discuss, that is what Davison-Germer experiment. Okay, right. And regarding the photoelectric effect, when the invisible form of energy, that is light, incident on a metallic surface, the emission of electrons takes place. So this phenomena is called as photoelectric effect. And here, in this case, we have to discuss three important definitions. One is work function or threshold energy, right? So work function is the minimum energy of incident radiation required to eject the electrons from metallic surface, right? And threshold frequency is the minimum frequency of incident radiations required to eject the electron from metal surface. Okay, and threshold wavelength is the maximum wavelength of incident radiation required to eject the electrons from a metallic surface. Okay, afterwards we discussed Hedge and Hallberg-Leonard observations. Thereafter, Einstein's photoelectric equation, that is what E is equal to W naught plus K maximum. Okay, there itself we discussed about the effect of intensity and frequency regarding photocurrent. Okay, so as we discussed, intensity is directly proportional to the number of incident radiations, right, number of incident photons. Okay, anyhow, E is directly proportional to the number of emitted photoelectrons per time. E is directly proportional to the photocurrent. E is directly proportional to the 1 by distance square by keeping frequency as a constant. When we are studying effect of frequency, we assume that the intensity is constant. There, as the frequency of light increases, the stopping potential increases, but there is no change in the photoelectric current. Okay, right. Afterwards, we discussed the important formulas, and then we went to discuss, that is, particle nature of light. There itself, what is photon and what is the energy of the photon? That is, E is equal to h nu, that is equal to hc by lambda. Afterwards, mass of a photon, that is m is equal to E by c square, and momentum of the photon, then number of emitted photons, intensity of light, number of photon falling per second. Number of photon falling per second, that is what n is equal to P by E. So, P is the power of radiation and E is the energy of photon. Energy of photon. Okay, right. Thereafter, we discussed wave nature of light. Wave nature of light. And while discussing the wave nature of light, the important quantity, we discussed in our previous class, de Broglie wavelength. That is what can write in terms of Planck's constant and momentum, that is what lambda is equal to h by p. That you can also write in terms of mass and kinetic energy, that is what h by square root of 2 me. H by square root of 2 me. Okay, and h is the Planck's constant, m is the mass of the particle, v is the speed of the particle, and E is the kinetic energy of the particle. Okay, right. Thereafter, we had expressions for de Broglie wavelength associated with the charged particles and uncharged particles also. After that, we discussed the characteristics of matter waves. Characteristics of matter waves. Okay, and this is the information from the starting of this chapter till this class we discussed. Okay, in continuation to this, we are going to discuss Davison-Germer experiment. Okay, so you please be focused, and what is the experiment and what is the conclusion of the experiment? What is the conclusion of the experiment, right? So regarding Neet point of view or JEE mains point of view, in every class, whatever the chapter, we focus on the quantities, the new quantities what we are going to get, and that particular quantity depends upon what factors, and then what are the relations we got. Relations means just like a formula, right? And regarding those particular quantities, what are scalar quantities and what are vector quantities, right? So that and all very important for us regarding the competitive point of view. Okay, right. See here, Davison and Germer experiment. It is used to study the scattering electron. It is used to study the scattering electron from a solid or to verify the wave nature of electron, right? So as simple as such, he is saying that it is used to study the scattering electron from a solid or to verify the wave nature of electron. You know very well when the electron is going to hit, right? When the electron comes out, right, from a solid, I mean just by bombarding, right? Otherwise, if you take a metallic surface, when the metallic surface is going to expose to the electromagnetic radiation, that is what light, the emission of electrons takes place, right? It is what photoelectric effect. So this Davison and Germer experiment used to study the scattering of electron from a solid or to verify the wave nature of electron. Okay, right. A beam of electrons emitted by electron gun. A beam of electrons emitted by electron gun is made to fall on nickel crystal cut along the cubical axis at a particular angle, right? A beam of electrons emitted by electron gun is made to fall on nickel crystal cut along cubical axis at a particular angle. Okay, right, full stop. Nickel crystal behaves like a three-dimensional diffraction grating. nickel crystal behaves like a three-dimensional diffraction grating and it diffracts the electron beam obtained from electron gun. Nickel crystal. So he is talking about the role of nickel crystal in this experiment. That is what nickel crystal behaves like a three-dimensional diffraction grating and it diffracts the electron beam obtained from electron gun. It diffracts the electron beam obtained from electron gun. Okay, right. After this, you see this, that is what situation, what happens or what took place while doing the experiment. That is what here, which is nickel crystal. See here, which is what electron gun, it is the filament and this is the path in which the electrons are coming, right? So it is the detector. It is the detector and through this detector is going to detect. The purpose of detector is to detect the electrons, okay, right? And you see here, this is what I already told you, which is the filament and electron gun. The electron beam is coming and this is called as incident beam of electrons. Incident beam of electrons, and this is the way after completion of incident the electrons are going to reach the detector. So which is also called as diffracted beam of electrons. This is called as diffracted beam of electrons and this is what phi, right? And when it is theta, according to geometrical mathematics, and this is also theta, right? So when it is theta, this is also theta and this is called as phi, and this is what like 180, right? This is what like 180, right? Okay. And here what he is saying is the diffracted beam of electrons, is received by the detector which can be positioned, right? The diffracted beam of electrons is received by the detector which can be positioned at any angle by rotating it about the point of incidence. I will repeat once again. The diffracted beam of electrons is received by the detector which can be positioned at any angle by rotating it about the point of incidence. So what he is saying is the detector is movable. The detector is movable detector. So wherever you want, you can keep the detector, right? Wherever you want, you can keep the detector. So at whatever the angle we want, you can keep the detector. That he is saying about the point of incidence. This is what point of incidence, okay, right? And the energy of the incident beam of electrons, can also be varied by changing the applied voltage to the electron gun. The energy of the incident beam of electrons can also be varied by changing the applied voltage to the electron gun. Okay, that's because electron gun is the source for electron beam. That is what incident electron beam. Okay, so that is in our hands. By changing the applied voltage to the electron gun, we can change the energy of the incident beam of electrons. Okay, right. Next, third point, see here. According to classical physics, the intensity of scattered beam of electrons, according to the classical physics, the intensity of scattered beam of electrons at all scattering angles, according to classical physics, the intensity of scattered beam of electrons at all scattering angles will be same, right? You just observe carefully, this is the point. I will repeat once again. See here, the point is he mentioned the thing, that is what according to classical physics, the intensity of scattered beam of electrons at all scattering angles, right? At all scattering angles will be same, but Davison and Germer found that the intensity of scattered beam of electrons was not the same, but different angles of scattering. But different angles of scattering, right? You just see here, see the light. According to classical physics, the intensity of scattered beam of electrons, at all scattering angles will be same. This is one point, right? But continuation is there, right? There is no full stop, but continuation. But Davison and Germer found that the intensity of scattered beam of electrons was not the same, but different angles of scattering. Okay. It is maximum for diffracting angle 50 degrees at 54 volt potential difference. It is maximum for diffracting angle 50 degrees at 54 volt potential difference. Here two things are happening. One is classical physics perception or classical physics point of view. Another one is the scientist Davison and Germer point of view, right? So both are contradiction. So according to classical physics, the intensity of scattered beam of electrons at all scattering angles will be same. But Davison and Germer found that the intensity of scattered beam of electrons was not the same, but different angles of scattering. So as simple as such, in one case, according to classical physics, no relation between intensity of scattered beam of electrons and scattered angles. But according to Davison and Germer, there is a relation. That he is saying, and he also told that it is maximum for diffracting angle 50 degrees. At 54 volt potential difference. Okay, right. After that, see here, fourth point. If the de Broglie waves exist for electrons, then those should be diffracted as X-rays. If the de Broglie waves exist for electrons, then those should be diffracted as X-rays. Okay. Using the Brach's formula, another scientist, Brach. Using the Brach's formula, 2d sin theta is equal to n lambda. 2d sin theta is equal to n lambda. And we can determine the wavelength of the waves. That is what lambda is here now. Right. And what is d means, which is the distance between diffracting planes. D is the distance between the diffracting planes, and theta is also there. Theta is equal to 180 minus 5 by 2. 180 minus 5 by 2. Okay. I will show you the graphs. You just observe. See here. I will show you the graphs. So that's what I drew here. See this. So these two things, right? See, it is what the incident beam, and it is the 54 volts, and it is 50 degrees, which is 50 degrees, right? And you see the third point lost. So what he is saying, right? It is, I already told you just now, it is maximum for diffracting angle 50 degrees at 54 volt potential difference. So you can see here, it is what 54 volt, and it is 50 degrees, right? And finally, this is the graph, right? So like this. Next, you can also see this graph, which is what is phi and what is theta and what is d, right? Atomic planes and incident and scattered or diffracted. Here it is what the theta is equal to 65 degrees, right? So these two are the things which gives information about the angles, okay, the angles of scattering and the potential difference. That is what 50 over potential. And I already told you in the first point, in the second point. What he told, the energy of the incident beam of electrons can also be varied by changing the applied voltage to the electron gun. Okay. So you just see here, it is what 54 volts potential difference we are maintaining. Now you see this formula, that is what 2d sin theta is equal to n lambda. 2d sin theta is equal to n lambda, and that is what Brach's formula. that is Brach's formula. Here d is the distance between the diffracting planes, right. Next, here theta is equal to 180 minus 5 by 2. Theta is equal to 180 minus 5 by 2, and that is the glancing angle for incident beam. What is meant by glancing angle, ma? So it is the angle between incident ray, that is what here, incident electron beam, and the plane of incidence, right. So this definition I told you when I was explaining the ray optics chapter, especially the phenomena of reflection, right. So there itself I told you what is angle of incidence and what is glancing angle of incidence, like that, right. So here theta is equal to 180 minus 5 by 2, that is the glancing angle, right. That is the glancing angle for incident beam, that is equal to Brach's angle, because the theta is present here, no, that is what the Brach's angle, okay. And if you talk about the distance, that is what small d, the distance between diffracting planes in nickel crystal, the distance between diffracting planes in nickel crystal for this experiment is d is equal to 0.91 angstrom unit, 0.91 angstrom unit, and the Brach's angle is equal to 65 degrees, right, 65 degrees. This gives, for n is equal to 1, the value of lambda is 2 into 0.91 into 10 to the power of minus 10 sine 65 degrees. That is equal to, if you do this calculation, you know the value of sine 65 degrees, right. So by substituting this value, and if you do this calculation, we will get it as 1.65 angstrom unit, 1.65 angstrom unit, okay, right. And you just compare the value from, that is what determined by using the formula. Now the de Broglie wavelength can also be determined by using the formula, that is what in previous class we discussed, that is lambda is equal to 12.27 angstrom unit divided by square root of applied voltage, that is 54. So finally which is equal to mathematically 1.67 angstrom unit, 1.67 angstrom unit, okay. Thus the de Broglie hypothesis is verified, okay. And you see that clearly, and one is 1.65 angstrom unit in one case, and in the second case which is what here 1.67 angstrom unit, 1.67 angstrom unit, okay, right. Thus the de Broglie hypothesis is verified, and the next point, fifth point from Davison-Germer experiment, the Brach's formula can be written in the form containing interatomic distance capital D and angle phi, So how can you write? This is 180 minus 5 by 2 means that you can write like this, 90 minus 5 by 2, and small d is equal to capital D cos theta, and if you take the component, then that is also equal to capital D sine phi by 2, right. Using sin theta is equal to cos phi by 2, 2d sin theta is equal to 10 lambda, which is the Brach's formula, that is equal to 2 into, in place of small d you write this value, and in place of sin theta you write this value, right. This side is n is equal to 1 and lambda is as it is. Then finally we will get it as d sin phi is equal to lambda, capital D sin phi is equal to lambda, right. So this is what wavelength in case of, that is Davison-Germer experiment. So according to the Brach's formula, and you can write. So we calculated that wavelength in different cases, that is what here and here and here also. So this is like what writing in terms of another thing, that is what here we have written lambda in terms of, that is what atomic distance, interatomic distance capital D, okay. And you see here, once I will give you overlook about this class, Now I explained each and every point clearly. Now I am going to give overlook, right? Observe carefully. In the first point, he is talking about the situation and role of nickel crystal, right? So role of nickel crystal is behaves like a three-dimensional diffraction grating, and it diffracts the electron beam obtained from electron gun. So what is the role of nickel crystal? Just giving diffraction to the electron beam which is going to incident on it, right? Second point is talking about the detector and the relation between energy of the incident beam and applied voltage, right? So what he is saying is, the detector what we are using here is movable detector. So wherever you want, there you can focus, at whatever the angle you want you can focus. And the applied voltage, if you change the applied voltage, automatically you can change the energy of the incident beam, right? Third point is, according to classical physics, the intensity of scattered beam of electrons at all scattering angles will be same. But according to Davis-Germer, it is not. So Davis-Germer found that the intensity of scattered beam of electrons was not the same, but different angles of scattering, right? It is maximum for diffracting angle 50 degrees at 54 volt potential difference, okay, right? And fourth one is talking about Brach's formula, that is 2d sin theta is equal to n lambda. And two ways we found. One is according to Brach's formula, that is we are getting as 1.65 angstrom unit, 1.65 angstrom unit the wavelength. And according to the previous in our previous classes we discussed, that is lambda is equal to 12.27 angstrom unit by square root of v. According to that we are getting 1.67 angstrom unit. So that we verified de Broglie hypothesis, okay. And next in the last point, that is what conclusion, okay. So we have written, that is wavelength in terms of interatomic distance also, right? 5 we already used, but in terms of interatomic distance also you can write the expression for wavelength, okay, right? So this is about Davis-Germer experiment, and rest of the part we will continue in the this is over. Davis-Germer experiment is over, okay. But the next continuation thing, whatever it is, we will continue in the next class. Thank you.